Welcome to another part of the ISM Statistics 1 exercise set, this time with an exercise on measures of contingency. Let's take a look at the exercise. A hotel conducts a survey to find out which service unit is favored by its guests. The answers have been split according to the guest's gender. During the first month, the dataset below has been collected. Use a suitable measure of association scaled to the interval 0 to 1 to quantify the strength of the association between the guest's gender and their evaluation. Well, first off, which type of contingency or correlation measure, in general, which measure of association can we use here? Well, obviously, gender as well as the service units are both nominally scaled variables, so the only thing which actually can be applied here is the chi-squared statistic or whatever is based on the chi-squared statistics, like the contingency coefficient or its corrected pendant. So as we also have the task here to find a measure of association scaled to the interval 0 to 1, it couldn't be chi-squared, so it needs to be the corrected contingency coefficient. So we will aim to get this. What are we going to do with this? First off, we take our table and extend this for the marginal frequencies. So we add one column and one row, and in those we just put the sums of the corresponding row or column. So for example, for the first one, we can add all the numbers for male, and we will get a total of 80 male participants. If we do the same for female, we will get as well 80 participants. And then we can do the same thing for each of the units. So 22 mentioned the reception, 73 mentioned the room service, and 65 mentioned the restaurant or the bar. Here you have one possibility to check whether you calculated correctly, because if we sum up any of those two sums, in the end we'll need to arrive at the same result here of 160 observations, 160 people who have been interviewed in total. So this is the first step, and we need those marginal frequencies for the next step, because in the next step we need to calculate the expected frequencies. Well, while this formula looks somewhat cryptic, it becomes relatively easy if we take a look just as our frequency table, our cross table we had before. However, in this case we only consider our marginal frequencies and we leave blank the cells in between, because in these we will now calculate the expected frequencies. How are we going to do this? We are always, for each cell, take the marginal frequency according to the row and according to the column, multiply them with each other and divide them by the overall total amount of participants or of observations. So for example, for male and reception, we multiply 80 and 22 and divide this by 160. We do this, we get as a result 11. Similarly, if we do the stuff for mail and room service, we multiply, as seen here, 80 and 73, and again divide this by 160. And we do the same for restaurant, bar, and mail. Here, the only thing which changes is the marginal frequency according to the row. So the only thing different here is the 65. And then we do the same thing for females, and well, as we can see here, we will get exactly the same results, owing to the fact that male and female have the same marginal frequencies. So that's the reason why they don't differ in any which way. However, well, we can calculate this way, then we can check whether we did this correctly by checking whether all the sums work out. But in the end, well, they should. So we need as well those expected frequencies we just calculated as the original values, because the chi-squared statistics is just defined as the difference between those two values. How does this look in detail? Well, to calculate the chi-squared statistic, as I said, we take the actual and the expected frequencies. Here they have been summarized in one comprehensive table. And, well, we use this formula. This is not as complex as it might seem on first glance. We just calculate actual value minus expected value. So here we have like 10 minus 11 for male end reception. This difference is squared and then divided by the expected frequency. So again by 11. And if we were to do this for all of them, we can see here the second one, that's for reception and female. Here we calculate, or can also do this the other way around. Here we calculate 11, so the expected value minus the original value, all of this squared, divided by the expected value. The same thing for all the other 4 parts. In total, we have 6 parts because we have 6 different cells in our cross table, in our contingency table. So this is one possibility to check if maybe you've overlooked something. You need to have 6 different terms, one for each of the cells. So, and well, if we enter this large part into a calculator, we get as an end result 42.079. So this is the first part. Well, we can obviously see this is no value which lies somewhere in the interval 0 to 1, so we need to rescale this. The first part we can do in this context is by calculating the contingency coefficient. The contingency coefficient assures that the amount of observations does not bias our result. How could this bias our results? Well, obviously, if we have a larger amount of observations, there's more potential for the values, for the frequencies, to diverge from each other. So there's a larger potential for a higher chi-squared statistic. And that's the reason why we need to control for this. How to control for this? For this, first we take our chi-squared value and the following formula for the contingency coefficient k. So meaning we just take chi-squared, divide this by itself plus the number of observations. So here we have 42 point something divided by 42 point something plus 160. 160 being the total amount of observations. And when we calculated this fraction, we just get the square root from it. So here we get a value of 0.4563. This already looks better than the original chi-squared. However, the contingency coefficient also is not necessarily limited to the interval of 0 to 1, because there could be a problem with the size of the contingency table. Well, we argued with the chi-squared statistic that if we have more cells in our contingency table for the chi-squared statistic, we will add up more terms, meaning larger contingency tables have a higher potential to leading to a larger chi-squared value and thus to a larger contingency coefficient. So we need to control for the size of our contingency table as well. How to do this? This we can do by using the corrected contingency coefficient. And we get this one by first taking a look at what is larger. Is the number of rows or the numbers of columns larger? Here, well, we obviously see the smaller of the two. That's the number of columns. We only have 2 columns, whereas we have 3 rows, so number of rows is larger. So we skip the larger one. We calculate the minimum of both of them, and this in this case is 2. So we need the 2 to get our correction factor. The correction factor being 2 divided by 2 minus 1 and the square root of this. So here we have like the square root of 2 divided by 1, so the square root of 2 is our correction factor. This value is just multiplied with the contingency coefficient we got before leading in the end to a correlated corrected contingency coefficient of 0.6453. This then is a measure in the interval 0 to 1, and we see, as this is a comparatively large value, we can assume that there is some kind of strong or stronger relation, contingency, between a person's gender and its evaluation of the different facilities of the hotel. And this concludes also this exercise. I hope all of you enjoyed listening to this and were able to take something from it. So until next time, see you and goodbye.